Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I am the coordinator for the Shadow the Scientist initiative. And here we are. We have one member of the observing team joining us now. Raja.
I'm so sorry to be late joining. We are having some difficulties with the instrument and weather in Hawaii. So things are not going optimally. So please give me a few minutes and I will be back.
Okay, no problem, Raja. I was just about to check in with you all. Thank you.
Jamaica, I may have to leave the Zoom call, join that one and come back, okay?
Okay, Roger, when you come back, will you send me a message in the chat when you come back, just in case I don't see you? Thank you so much.
Okay, I'll send. I can do that in the chat, but when I come back, it'll put me in the waiting room, right?
Yes, you can message me from the waiting room.
Oh, I didn't know that. Okay, I'll do that.
Yes, right. I'll look for that, Roger. No worries. I figured you all were having potentially some weather because it is very rainy down here in Hilo, and Mauna Kea is in the clouds from my perspective here.
Yeah, so I can do a couple of things. There's a couple of possibilities. We're really having serious cloud issues, but I have other images I can share in the Virgo cluster, and we can run a shadow session just based on that. Would you prefer I do that, or would you, if you give me a few minutes, I can first go and check what's going on with the instrument and do both.
That sounds good. That sounds good, Roger. Please go ahead and check.
I'll come right back.
And we'll be right here.
Okay, thank you. Thank you all.
Okay. Okay, so in the chat right now is a link to the Mauna Kea Weather Center. If you click on that link, yes, you're so welcome. When you click on that link, you'll be able to see not only the weather forecast, but you'll also be able to see the webcams live. So let me just admit that person, and then let's take a look. So I'm going to share my screen. Let's see who it is. Okay, share my screen. So when you click on that link to the Mauna Kea Weather Center, there are many things you can see. In addition to the forecast, you can see live webcams. And this is a webcam from CFHT, that is the Canada, France, Hawaii telescope. And they are actually looking towards Gemini Observatory. So if you were with us in the CBSC session yesterday, this is the telescope that was being used during that session. This is the Gemini Observatory North. Now, as Roger was saying, they are dealing with some clouds. And you can see these clouds here. See the moon rising, but you can see that there's quite a bit of cloud cover. So I can go back and we can also see, let's check out some more. Okay, so this is a view from the Subaru telescope. Subaru is the National Astronomical Observatory of Japan. And as you can see, Subaru is open and on sky. There are some clouds over here. A great view of the night sky, gorgeous. And these two white domes here over to the left, where my cursor is, are the twin Keck telescopes. So the observing team tonight, which includes, of course, Raja GuhaThakurta, Eric Peng, and Elisa Toloba, they will be using one of these two telescopes. I believe they're using Keck II. I'm not sure. They're using one of the Keck telescopes. Now, they can work in concert as well, but very often they are working individually, these telescopes. So as Roger said, they're dealing with some weather here, and sometimes cloud cover, even though it looks beautiful out here, clouds bring moisture, and there is a threshold that the telescopes have to consider when opening the dome of the telescope. Thank you for your questions and comments. Welcome. So if you're just joining us, we are looking at the webcams. Yes, this view is live. This is a live view. Well, there may be a 30-second delay. So so if you look at the bottom here, you can see the timestamp. And these are typically live views. Okay. Nope, that is a not very good view of Keck telescopes. Let's try another one there. Okay, so these are time lapses, but this is a current view that's just 1 minute old. So this is the NASA Infrared Telescope Facility. Now, the NASA Infrared Telescope Facility is located to the lower west part of the summit region. You would look over and up to the west from IRTF to see the Keck telescopes, which are situated just beside the Subaru Observatory. Yes, again, this is a mostly live view. It's about 1.5 minutes old. Again, you can see the time here. And you can see this looks like one of the Ranger vehicles that are going around at the summit to make sure everything is all right, and just take an assessment of the area. As you can see, the clouds that Roger was talking about. Now, even though this is a beautiful view and it looks like maybe there's not too many issues with the clouds, clouds, of course, mean there is moisture in the air. We'll take a look again here. This is a view from one of the cloud cams of the Subaru telescope. This is the National Astronomical Observatory of Japan. And an interesting fact, if you look on the back of a Subaru vehicle, there are like 6 or 7 stars next to the Subaru vehicle symbol. Those 7 stars are actually represent an open cluster in the night sky called, among other things, Subaru. Is also known as the 7 Sisters or the Pleiades. And so that is the symbol for the Subaru vehicle. And so, of course, it makes a lot of sense that the National Astronomical Observatory of Japan would have the name Subaru, as that is a Japanese name for that collection of stars. I see we have Raja has returned. And so we can ask Raja to talk a little bit more about multi-messenger astronomy and gravitational waves once he is back on screen. So let me just give him co-host privileges. And Raja, are you with us?
I can unmute now, yes. Sorry,
Okay.
sorry everyone. So I've
No
been,
worries.
and Jamaica, just in the interest of time, I sent my Zoom link to Eric, Elisa, and Rosalie. And so if they join, they'll change their names. They'll change their Zoom names.
Okay, sounds great, Raja. I'll be on the lookout for more Rajas so I can be sure to
Exactly.
let them in. Okay,
Very-
so thank you for coming back to us, Raja. While you were gone, we were having some interesting conversations about gravitational waves, about LIGO, the Event Horizon Telescope, and seeing the light around the event horizon. We were also looking at the Mauna Kea Weather Center and the live webcams to see what the weather is like. So maybe you could start there with the weather there above the Keck telescopes and what's the current status of the instruments you're using.
So there are quite a few clouds over Mauna Kea right now. And my colleagues and I are starting to take data, but there are occasional breaks in the cloud. But it's been quite unpredictable exactly. I'm going to turn my camera around, sorry, so you can get a slightly better lighting. Okay, is this better? Light's better now?
Yes, that's
Okay.
great. Thank you, Raja.
Yeah, so we are sort of dodging clouds and looking at really bright stars that are bright enough so they can get enough light through the clouds. It has just started to clear. The clouds have started to break a little bit. So we are hopeful that we'll be able to get some better data. There are a couple of things we can do while we're waiting for Eric and Elisa and Rosalie to join. One of the issues I was having is I couldn't get the instrument control software running on my laptop. This being a new laptop, I'm trying to troubleshoot that. Without that, I can't share. I can share my screen, but I can't. You wouldn't get to see what the observers are seeing on their control computers, on the telescope control computers. What I can share with the group are images of galaxies in the Virgo cluster that our group has taken in the past, and we can use that to, we could certainly use that to, talk about galaxies and what they look like. I can share my screen and do it that way.
Yes, you should be able to share your screen, Raja.
Thank you. What screen should I share? Okay, I'm going to share
And so I'll say to everyone, if you have questions like you have been doing, please continue to drop those in the chat and I will try to highlight them for Raja. Raja will, look through the chat, but I will also try to bring his attention to them when he has time to answer. So please continue, and we appreciate your patience. Thank you.
What are you seeing on the screen right now, Jamaica? Are you seeing like a set of red squares?
Yes.
Okay, I'm going to zoom in a little bit using this plus button. This is like almost like a Google map or any kind of map application, except you're looking at a map of the sky. And I can, of course, remove these grids if we wanted to. Let me see if I can remove these easily. Show grid. Let me remove the grid instead. There we go. That went away. Show pointings, show individual images. Let me remove these just to clear up the, yeah, there we go. Much better. If I put, basically what you're seeing is a region of the sky that was imaged not all at once, but as a series, as you can see here, series of squares, each one marked in red. And to give you a sense of scale, if you were taking a picture of the full moon, you could fit 4 of them into each square. So that's how much of the sky is being imaged here. So each square is 1 degree by 1 degree. and the full moon subtends half a degree in diameter. The diameter of the full moon is, the angular diameter of the full moon is half a degree. So basically, you could fit 4 full moons. If you can see my cursor, you could fit 4 full moons in a 2x2 grid within each of these squares. There are over 100 of these red squares that make up this survey. If I zoom out a little bit, you'll see that there's well over 100. I think there's 117, if I'm not mistaken, 117 of these squares that make up this grid. You know, there you go. Now it's showing the whole grid. So tonight we are studying a few of the galaxies that are within this red imaged region. This image was taken with a telescope in Hawaii on the same mountaintop that that is also host to the telescope we are using tonight. So what I'm trying to say is there's a mountaintop on an island in Hawaii that contains many telescopes. One of those telescopes was used by our team to take this set of images, and a different telescope is being used tonight to study some of these galaxies in more detail. So let me zoom in. I'm going to remove this grid and I'm going to zoom in a little bit. I'll show you what some of these galaxies look like. Just give me a moment. Yeah, it takes, because it's a very big file, it takes a few seconds to go from the grid appearing to the grid disappearing. Even when I click the button to say remove the grid, it takes a few seconds.
Roger, many people in the chat are welcoming you and are very happy that you have joined. Thank you.
Thank you. I would let me zoom into a few galaxies. Actually, I'll zoom into one of the galaxies that I absolutely love. It's a beautiful galaxy. I can recognize it from a great distance. My cursor is pointing at it right now. I'm going to zoom in and you'll see why I like it so much. It's a spectacular galaxy. Let me get this zoom bar out of the way a little bit. And I'm going to check in to see if Elisa and Eric are able to join, and Rosalie and Max. There are 5 of us working together tonight on this research project. I'm going to zoom in one more time. Look at this beautiful galaxy. It looks like a mess. It looks like a train accident. But this galaxy, with the very bright center and these wisps all around, is actually being distorted by the what's a good analogy for it? This galaxy is falling into this group of galaxies, or into this cluster of galaxies, and while it's falling in, it's experiencing some what is called ram pressure, in the same way that if you're in a car that's moving, and if you stick your hand out of the car, the fact that you're moving into, moving through the air on Earth, if your car is driving, there's air around you, that air creates a strong wind that's pushing your hands back if you try to stick your hand out of the car, out of a moving car. I don't recommend doing this. It's dangerous, of course, to stick your hand out of a moving car, but it's the same phenomenon that this galaxy is traveling at high speed relative to the cluster of galaxies. It's falling into the cluster because of the gravity of the cluster. And it's experiencing this very strong push from the material in the space between galaxies. There's something called the intergalactic medium. It contains charged particles, plasma, and that's pushing on the material in this galaxy, causing it to get stretched out like this. It's a rare phenomenon. You see most galaxies aren't going through that, but this one is. Would it be? Yeah, Tamika.
While you're looking at this galaxy and talking about all the larger view in the context of your research project, We have a question. We have many questions, and so please keep those questions coming. We do have I get the transcript of all the questions, and I can certainly pass them along to Raja and the research team, and we can answer them and post those answers under the description for the of the edited recording for this video. But one question from Arnav, what are the goals of your research project that you all are working on?
I will answer that in a moment. I'm just sending, I stopped my screen share so I could send Eric, Elisa, Rosalie, Eric, and Elisa an email to okay, I'm back. I'm back with you guys. What are the broader goals of this research? We are in the project we are doing tonight. It's part of a set of 4 nights that have been awarded to that have been allocated to this project. We had one night in March 26th. We have one night tonight. We have a night tomorrow night, so that's 3 nights. Then we have a half night in late May and a half night in early June. So we have 3 full nights and 2 half nights. And if you do the arithmetic, 3 full nights and 2 half nights add up to the equivalent of 4 nights. Now, what we're trying to do across these 4 nights, not just tonight, but across all 4 nights, is study a particular class of galaxies. And I'll put that kind of galaxy's name in the chat. They're called ultra-diffuse galaxies, UDGs. UDG is the abbreviation. If you're feeling lazy and you don't want to say the whole phrase, you'd say UDG, but they're called ultra-diffuse galaxies. I'll just put it in the chat. So that particular galaxy that I was showing you, I don't remember its name. Typically, galaxies don't have names given to them. They have numbers assigned to them. And that galaxy is quite famous, but it still doesn't have, if it has a name, I'm not aware of it. It has a number. But okay, so we're studying ultra-diffuse galaxies. And why are we studying this class of galaxies? Okay, so I'll try to explain that briefly. In many sciences, astronomy included, biology, many sciences, you look at trends or correlations between 2 quantities. For example, if you were to make a plot of the age of a human being on one axis and their height on the other axis, age versus height. If you made a diagram like that, or let's say age versus weight, age versus weight or age versus height, either one. Let's do age versus height. If you made a plot like that, let's say for all people on this earth, what would the graph look like? Can people start to describe that a little bit? That is, for every person, you would put a dot on that graph corresponding to, if you have age on the x-axis and their height measured in meters, say, on the y-axis, what would that look like? I know it's hard for you to write that in the chat, but when the age of the person exceeds, I don't know, 15 years, my guess is the graph would go horizontal. That is, the set of points would have some range to them because not everyone is the same height when they're over 15 years old. Some people are very tall, some people are short, but most people are somewhere between 5 and 6 feet tall. So you'd get a broad band where the height would not change as a function of age because people don't keep growing in height beyond a certain age, 15, 15-ish, maybe 20. Some people grow until a little later. Some people stop growing earlier, but I think you would see something like that. But at younger ages, between say 0 and 15, you would see an increasing trend. As people get older, they get taller. So that's an example of a trend that is caused by biology, the biology of human beings and how we grow over time. If you make, you can make similar plots for physical systems or astrophysical systems. You can make plots for galaxies. So one of the plots people make is how luminous or how bright, how intrinsically bright is a galaxy. That is how many times brighter is it, how many times more luminous is it, say, than the luminosity of the sun. If you plotted that on the x-axis, how luminous is the galaxy? And on the y-axis, you plotted its size. How big is the galaxy? Almost like our age and height diagram, except this time it's for galaxies. And on the x-axis is how much light it's emitting. And on the y-axis is its size, almost analogous to a human being's height. So its size meaning its diameter. Diameter of the galaxy on the y-axis, and the luminosity of the galaxy, how much energy it's putting out per unit time, watts or ergs per second, whatever units you want to measure in. If you want to measure in CGS units, it's ergs per second. If you measure in SI or MKS units, it would be watts or joules per second. That's the x-axis is the energy per unit time, and the y-axis is size, let's say in meters or light years, whatever unit you choose. If you chose that, galaxies show a trend. As you get to more and more luminous galaxies, they tend to be bigger and bigger. But what people have found is it's not a very thin trend line. It's, in fact, there's quite a lot of spread. While there's a trend line, there's a lot of spread. In other words, if I go to a particular level of brightness, particular luminosity, galaxies have a range of sizes. And the galaxies we are studying tonight are larger than the average galaxy of comparable luminosity. So for their luminosity, these galaxies are unusually large. That's why they're called ultra-diffuse. The light is very spread out compared to other galaxies of comparable luminosity. That was a long explanation.
That was a brilliant explanation, Raja. Thank you for that. And kind of along those lines of the research that you and your team are doing, I have a question about your specialized skills in advanced optics and dark matter. Could you briefly talk about that in connection to maybe galaxies and the large-scale structure of the universe?
I would be happy to, Jimika. I didn't completely understand the question. Do you mean what I've studied so far, going back, or I didn't completely catch that. Sorry.
Yes, no, the question, there's a statement here that they're very interested in your profile. They looked you up and they got to know that you have specialized skills in advanced optics and dark matter, and they would like to know more about these two topics. And so I thought you could connect that to the large scale structure of the universe and structure of galaxies, dark matter in particular, and then how your background in optics in general is helpful in all of the research that you do.
Sure, I'll do my best. The way people study dark matter, one of the ways in which people study dark matter is to study how fast stars are moving inside a galaxy. Meaning, we talk about galaxies spinning. Galaxies spin like frisbees, but another way of thinking about it is the stars in a galaxy are going around in circles. They're going around the center of the galaxy, and the speed at which stars move during their rotation around the center of the galaxy is determined by how much gravitational force they experience. You know, the speed at which Mercury goes around the sun is related to the force that Mercury experiences, the gravitational force Mercury experiences due to the gravitational pull of the sun. The force at which the sun pulls on the Earth determines the speed at which the Earth goes around the sun. Same way, in a galaxy, there isn't a single object at the center, like the sun in the solar system. There isn't a single object at the center of a galaxy that is causing this gravitation. It's the collective material, all of the material together, all the stars, all of the material, if there's things other than stars, all of the material together, their collective gravity, their collective gravitational force is what the stars are responding to when they're spinning. Now, using very simple Newton's laws of gravity, you can construct an equation and create a very simple equation, and I'll write the equation in the chat. It's an equation. Let me see if I can write this in the chat very quickly. Jamika, I'll write this to everyone.
Perfect.
I've just written an approximate equation in the chat that says m equals v squared multiplied by r divided by g, where g is the gravitational constant. Capital G is the gravitational constant. Some of you may have encountered that already in school, what capital G is. M equals v squared r over g. V is the speed at which something is rotating, and which star is the speed of its orbital speed around the center of the galaxy is given by v. R is the radius of the orbit, and capital G is the gravitational constant. M is the collective mass of the galaxy whose gravitational pull the star is responding to. Now, before I go any further, I'm going to write the force of gravity between two objects in the chat. And I would, are students able to raise their hand in this Zoom setting, Jamika?
Yes, they can raise their hand.
Okay, so please raise your hand if you recognize this as an equation. I'm about to write the equation. Do people recognize this formula that I've just put in the chat? F equals G M1 M2 over R squared. So I encourage people.
I see lots of hands raised.
Lots of hands raised. Do we have a sense of how many hands? I'm looking at that. Lots of hands raised.
See. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and we have 3 yes sirs in the chat. 9, 10, 11. Another hand 12, 13 from
More hands are going up. Very good.
Kayati, yes. Annika.
Okay. So this formula, which is people are typing so fast into the chat that it is disappearing. My formula is disappearing into the. So just give me a moment. I'll type the formula in one more time. Okay. So a lot of people know this formula. Okay, so this is the force between two objects. M1 and M2 are their masses. R is the distance between them. Okay. I'm going to put one more formula in there, which is for the formula for centripetal force. Okay. F equals, G is the gravitational constant. I'm going to put a formula for centripetal force, mv squared divided by R. How many people are familiar with that? Show of hands again, please. Lots of people. Very good. Very good. Very good. We're in India. Of course, we know EM. What does that mean? Okay. F equals, the centripetal force is mv squared over R. and the gravitational force is Gm1m2 over r squared. Okay, so now imagine that capital M, I'm going to write the force formula in a slightly different way. Instead of writing M1 and M2, I'm going to pretend that capital M is the mass of the sun, and and lowercase m is the mass of the planet. Okay, so then the gravitational force between them is the mass of the sun, capital M, multiplied by the mass of the planet, lowercase m, divided by radius squared. Now, I can also write for the planet that the centripetal force is equal to lowercase m v squared divided by r. If I then combine these two formulae and say the two forces are equal, the gravitational force is equal to the centripetal force. If I set them equal, you'll notice that capital lowercase m cancels out. If I set the right-hand sides of the two equations equal to each other, the lowercase m cancels out, yes? And you get, if you then, after you cancel out lowercase m, if you solve for capital M, you get m equals, one of the r's cancels out. Oh, I forgot the g in the formula, sorry, my bad. In the force formula, I should have typed this. Just give me a moment. I'm going to type out the whole thing. If I take these two equations like this and I combine them, if I set those two forces equal, from that I can derive m equals v squared r over g. So basically, the first equation is the force between the sun, whose mass is capital M, planet, whose mass is lowercase m. Their gravitational force is G, capital M, lowercase m, divided by r squared. The second formula is the centripetal force required to make an object move at the speed of v at a radius of r, circular orbit, where m is the mass of the planet. So if you set the two forces equal and you solve for capital M, you get capital M, mass of the sun, is equal to v squared r divided by g. This formula, are people comfortable with this formula? Can I have a quick show if you lower your hand and re-raise it to tell me if you're comfortable with this formula? Yes, lots of people. Fantastic. So capital M this formula is extremely powerful because by measuring how fast stars are rotating around a galaxy, we are measuring V. We know the radius of orbit of the star. So we know R. So V squared R divided by, we know the gravitational constant. So V squared R divided by G gives us the total mass of that the star in the galaxy is experiencing. The overall mass that it's experiencing, not just of a single point, but of all the things in the galaxy that are pulling on it. So a very famous scientist named Vera Rubin, I'm going to put her name in the chat, very famous scientist who I've had the privilege of meeting many years ago. So Vera Rubin, she's famous for measuring how fast galaxies were spinning. So she measured this for the Andromeda galaxy. She measured this for other galaxies, and in all cases, she was able to calculate the total mass m of a galaxy by measuring v squared using Doppler shift. She was measuring the rotation of the galaxy. She could measure the radius of the galaxy from the images of the galaxy. So v squared r divided by g, she was able to calculate, and she found that these galaxies, the mass they contained, was more than you would infer from the light they're emitting. If you assumed we made the reasonable assumption that the light they're emitting is coming from stars, which is accurate. The light of a galaxy is produced by stars. If you make that assumption, then you can make a reasonable estimate for how many stars the galaxy contains, how much mass is contained in the form of stars. And she found that there was a mismatch between how much mass you would infer from the orbits of stars. This is how much mass you would infer just by looking at how much light a galaxy puts out. So based on the light of a galaxy, you would conclude it had a certain amount of mass, but based on the orbits of the stars, you would conclude it had much more mass than you were getting from the light of the stars. So she made the logical conclusion that there's something in galaxies in addition to their stars. The stars are producing some gravity, but there's something else that must be producing gravity. So, in fact, the stars alone make up, she found the stars alone make up only 10% of the mass of the galaxy. The remaining 90%, roughly speaking, is coming from some other material that we can't see. That is what dark matter is. Jamika, that was a very long explanation.
No, that was fantastic. And while you were doing that, I dropped a link in the chat so that people can read up a bit more on Vera Rubin if they weren't familiar with her groundbreaking work on dark matter. We did have a few people say in the chat that they're in some of the lower grades. I believe saw a couple of grade 7s, and so they weren't very familiar with the formulae that you were discussing, but I see that we've had several people very kindly explain those in the chat. But if you'd like to give a quick summary of those 3 formulae again, I'm sure it would be welcome.
Yeah, so I think for the younger students in the group, when you study physics in your later classes, in your later grades, this is something that you will certainly encounter. You'll encounter how the force between 2 masses, you'll study the formula for the force between 2 masses. You'll study that from Newton's laws, that when an object moves in a straight line at a constant speed, then of course you don't need a force, because a constant speed in a straight line, how can I put it? Newton's laws state that in order to change the speed and or direction of an object, you need to apply a force. If you don't apply a force, it will move in a constant speed in a straight line. That constant speed could be 0. So an object is either stationary or moving in a straight line with a constant speed if there's no force acting on it. Conversely, if an object is moving in a circular path, that means there must be a force acting on it. And these forces and laws of motion, as Ariana has put in the chat, you'll learn about formulae, equations that let you connect how strong the force needs to be depending on the speed of the object and the radius of its circular path. It was indeed given by Newton. These are part of Newton's first, second, and third laws of motion. Can I get a sense of the age range of the students on this call today? Are there many people who are under the age of 10? Anyone who's under the age of 10, please raise your hand. No one? Okay. How about anyone over the age of 20? Any students over the age of 20? There may be teachers on the call, but are there any students? Probably not, right? Are there? Okay. Oh, Varshit, does that mean you're over the age of 20? Okay. So I'm guessing then that you are somewhere between classes 6, 7, 8 to class 12, something in that range. Sophia, did you have a question? Are you able to put it into the chat?
While we're waiting for that question, we have many people thanking you for that explanation. And here we have one question. First, there was one on the term called the Barycenter. They'd come across it in their studies and wanted to know its relation to celestial objects.
There's
How,
Elisa.
oh, okay. And then what is the relationship between dark matter and antiparticles?
Sorry, I just admitted Elisa. I hope you didn't mind that. She's
Oh,
one
I
of.
did. I clicked on it also.
Oh, you did. Okay. Is
Yeah,
she
but I'll admit everybody.
okay? Is she able to share her screen?
I'm working on it.
Oh, thank you. Thank you. Okay. And she'll be able to unmute, I assume, also.
So yeah, so that question on the
Yeah.
Barycenter.
So a barycenter is what is the barycenter? Let me see. I think it's the center of mass between two objects. If I'm not, let me look up the definition. Actually, I'm going to quickly look up this definition, so I'm not giving you. Hey, Elisa.
Hello,
Welcome,
Raja.
Lisa.
Hello.
Let's see.
Elisa, please, tell me what's going on with the observations.
Oh, it is a little bit crazy, so that's why it has taken me a while to connect here. So we're actually now observing our targets.
Really?
Yeah.
Ultra-diffuse galaxies. Okay, I was telling people about
Yes.
ultra-diffuse galaxies a moment ago.
Okay.
Ah.
So the clouds are there, but they're thin, so we can see through them a little bit. So we're just doing longer exposures than what we planned. But that's okay. So yeah, but we have to be monitoring the number of counts that we are receiving, so that if it drops, we stop, because we don't want to include that into our observations.
I see. And so this is an ultra-diffuse galaxy that you're taking red and blue side exposures on?
Yes.
Okay. Is there any chance you have your VNC running and you can share your screen?
I have it in the other computers. So the thing is that if I connect, we should figure this out, because I need to have two Zoom calls on, and then I need two computers, and everything is running in the other one.
I was just sharing the NGVS images of the Virgo cluster earlier, so I can always go back
I
to
think that we sent you some screenshots to show, so that you can show at least
Let me do that.
what we
Go
are
there.
looking at in the different desktops.
Okay.
I think
perfect.
Eric sent you that.
Yeah, I've got them. Let me show this off, and then we can talk through them. Elisa,
Okay.
we have a lot of students connected here. You can see there's 112 participants in the Zoom. If you look at the participant thing.
Yeah, wow. That's amazing.
We had even more yesterday. There are quite a few people.
Yeah. Very exciting.
Yeah. Please tell people a little bit about yourself, where you grew up, studied, and I'll do the same after you. And Jamaica, have you introduced yourself as well?
Yes, I introduced myself at the very beginning, just the basics. So yes, please, Elisa, and then Raja.
And then if Eric joins, we'll have him do the same for Rosalie. Go ahead, Elisa.
Okay, so I am originally from Spain. So I grew up in Spain, born and raised in Spain, and I did a degree in physics, and then I did a PhD in astrophysics, also everything in Spain, in Madrid. And after that, I got a fellowship to do a postdoctoral research, and I went to UCSC to work with Raja. So that's how we met back in 2011, I believe, yes. And it has been 13 years already. Yes. Yeah, and since then, Raja and I have been collaborating in every single project that we have been involved. Yeah.
And Elisa,
Yeah. Well,
yeah, sorry, you grew up in.
Yeah, no, and after that, I got professor position at University of the Pacific in California. So yeah, I stayed in the area.
And you were when you were growing up you were in Madrid and Granada also a little bit. Your grandmother was in Granada.
Yes, always in Madrid. I did all my studies in Madrid, but I have a family also in the south of Spain, in Granada. Yeah, my grandpa passed away, but he was also there, and my aunt and my cousins, and yeah.
And of course, it's a coincidence, but when my daughter was studying in college, she spent 6 months in Granada, where you have family living in Spain.
Yeah.
Now, let's see, Elisa, okay, so people on the call, many of them are students in school. There are some teachers on this call as well. And the term postdoctoral research may not be familiar. Even the term doctorate may not be familiar, but so it may be worth explaining if you want to, or if you want me to, I can do that also.
Yeah, sure. So, after high school, you go to college, you get your degree, you major in something. And after that, you can do study more, that is usually a master's, or a PhD that includes the master's as part of it. Master's is usually a specialization on a topic, 1 or 2 years, mostly classes, some project. PhD is usually like 4 to 6 years, is way longer. Classes usually first or the first, only 1 or maybe 2 years at the beginning, and then you have a very big research project that is going to be your thesis. So that is what the PhD is. So mostly, usually between 4 and 6 years after the degree. And after you get your doctorate diploma, at least in astrophysics, this is not true for all the sciences, but in astrophysics, you have to do independent research positions to then apply as a professor or as a staff member in an observatory. So during those years, that can go from like 2 to 4 or 5 years, you are basically leading your own projects and managing your own projects, getting the skills that you are going to need to then lead a line of research on your own, that then you will have, depending on what kind of institution you will have students, you will have postdocs working with you, or you will just collaborate in a more leading way because you have more skills in research, basically.
Thank you, Elisa. That's a very, very good explanation. So the term PhD and the term doctorate are often used interchangeably. In fact, the D in PhD stands for Doctor of Philosophy. That's what PhD stands for, Doctor of Philosophy. Capital P, lowercase h, and then capital D, usually with periods after capital P, lowercase h and a period, the capital D and a period. It stands for Doctor of Philosophy. It's the same as, that's sometimes called getting a doctorate. Now, you don't need to be a medical doctor. Medical doctors can also get a doctorate. They often get a degree called an MD degree, Doctor of Medicine. That's what MD stands for. Elisa and I, of course, have degrees that our PhDs are in astrophysics or physics, not in medicine. Now, any questions? If there are people who are thanking you, Elisa, for explaining insights and sharing your experience in Korea.
Sure, of course.
13 years we've been working together. We actually, after many years of trying, we have an NSF grant together.
Yes, finally.
The National Science Foundation of the US gives out money to researchers if they write a strong proposal. And Elisa and I have been trying, and we finally have a grant. We're coming up on end of year 2 of a 3-year grant. If any of you in this group want to study astronomy, astrophysics in college or get a PhD, then what you would do is focus on physics and mathematics, chemistry in your school years, and that prepares you for studying astrophysics in college, physics, astronomy, or astrophysics in college. I have the screenshots that Eric and you attached, so I can show that. Let me do that very quickly.
While you're showing your screen, we also had a question about if people wanted to study astrobiology or even astrophotography, what are some of the classes that would be needed outside the obvious?
So astrobiology is a very new field. So you would want to study the things I mentioned, so physics, mathematics, chemistry, but in addition to that, you'd want to study biology. For astro, it's a brand new field. It hasn't been around for very long. So there are biologists who are studying. There are people with training in biology who are doing astrobiology research. There are people with training in physics who are doing astrobiology research. If you wanted to be an astrophotographer, as far as I know, that is not so much of an academic degree. It's more of a hobby and like an artistic pursuit. I know some very, very good astrophotographers, but as far as I know, it's not so much of an academic degree. Elisa, what are we looking at here? We're looking at FACSUM, and is that a guider image in the middle?
Yes.
It's the magic image,
Yeah.
okay. So what you're looking at here, then for the folks on Zoom, these are the controls of the telescope. Sorry, controls of the telescope in Hawaii. The instrument we are using, the telescope we are using is called the Keck telescope, the second of the 2 Keck telescopes. That's why you'll see Keck II, where you see my cursor. FACSUM stands for Facilities Summary. FACSUM stands for Facilities Summary. It's telling us what direction of the sky the telescope is pointed in. It's telling us which galaxy we're looking at. NGVS stands for Next Generation Virgo Cluster Survey. UDG stands for ultra-diffuse galaxy. It's number 9 that we are studying. So it's a galaxy number 9. I was telling you earlier that we don't give names to galaxies, we give numbers. That's an example. There are lots of other numbers here. Some have to do with the humidity in the environment. Some have to do with the humidity graph is in the lower right. Then in this main rectangle where my cursor is, elevation means how far above the horizon the telescope is pointed. So it's at 53.76. So it's roughly close to halfway between pointing at the horizon and pointing at the zenith straight up. 45 degree would be exactly a halfway point. These are other angles. AZ stands for azimuth, EL stands for elevation. UT over here stands for universal time. When the snapshot was taken, it was in Greenwich Mean Time. It was 07 hours, 06 minutes and 24 seconds. LST stands for local sidereal time. It's the way you decide. It helps you understand what stars happen to be overhead at that moment. Anyway, there's lots of information on a slide like this. Eric sent me a few other snapshots, so let me go there. Let's see. Let me see. Yeah. This is, again, these very faint dots are stars that we are studying. I mean, we're not studying these. These stars are hitting the detector. This is interesting because we are taking these horizontal streaks these are different orders from different slices, right? Elisa, this is of a single star, I assume.
Yes.
Okay. So we're using a very unusual kind of instrument tonight, something called an integral field unit, IFU. And I'll put that in the chat, IFU. that's what it stands for is, I'm going to write this in the chat, integral field unit, IFU. You all know about a spectrum because a rainbow is an example of a spectrum of sunlight. In this case, in an IFU, instead of taking an image like you can with your cell phone, at every pixel in the image, we're getting a spectrum. We're getting a rainbow with many, many colors, more than just the 7 colors of the rainbow, with thousands of colors. So that's what an IFU does. Now, maybe I should take a moment to say a few words of introduction about my own path. Would that be okay to do?
Yeah, absolutely. Please do, Raja.
Okay. I think I mentioned to the group yesterday, and but some of you may not have been here yesterday. I grew up in Kolkata in India. And are there any people from Kolkata on this call? Oh, a few people from Kolkata. Fantastic. If you know which school you're from, please, you're welcome to type that into the chat. Central Kolkata. Very good. So I grew up in South Kolkata. I grew up in, you might recognize these places in Kolkata, Chorangi Road, Alipur, New Alipur, Baliganj. So I grew up in Kolkata. I went to I did all of my schooling there. I went to an elementary school first in New Alipur when I was a child. Then I went to La Martiniere for boys in, I guess, near Minto Park. What used to be called Minto Park is now called Shahid Bhagat Singh Udyan. So Minto Park is, La Martiniere for boys is right on Loudon Street or UN Ramachari Street. And on the other side is Rawdon Street, Sarojini Naidu Avenue. So I went to La Martiniere from class 3 to class 12. I studied science in class 11 and 12. And at the end of class 10, I did my ICSE board exam. At the end of class 12, I did my ISC board exam. And then I went from there to St. Xavier's College to study physics honors. So I had chemistry and mathematics as my past subjects in college. So I studied physics, chemistry, and mathematics for the first 2 years and only physics for the last year. And I got my BSc degree, Bachelor of Science degree. And after that, I studied at Science College in Kolkata. I went there to get a master's degree, but I left after 1 year. And I went to the US to get a PhD at Princeton University. And I spent 4 years, on getting a master's and PhD. And then, like Elisa was describing, I did postdoctoral research in Princeton, first at the Institute for Advanced Study, at the same institute where Albert Einstein had been a professor many years ago. How many of you have seen the movie Oppenheimer? Have some people seen the movie Oppenheimer? Probably not. It may be some people have. Okay. I don't know if it's R-rated and okay, many people have seen the movie Oppenheimer. Well, the some of the movie is shot in the Institute for Advanced Study where Oppenheimer was, he was a scientist there. So I was there for 3 years after finishing my PhD doing research, exactly as Elisa described. After your doctorate, after you finish your PhD, you spend a few years doing independent research, trying to develop leadership in some area of research. So I did that. I studied a few different things as a postdoc. I did 2 postdoctoral stints. Then I got a job in the city of Baltimore at the institute that runs the Hubble Space Telescope. I was there for a year, and even less than a year. I was there for 10.5 months. Then I left that to come to California to start a professor position there. And I've been there since November of 1994. So at the end of this year, I would have completed 30 years at the University of California, Santa Cruz. That's a long introduction.
That was a wonderful introduction by you both. Thank you for that background. We have quite a few questions and comments here in the chat. I'm going to pick out one here that's come up several times about the relationship between dark matter and antiparticle. What are their relations to each other? For Elisa, Raja.
There isn't an obvious relationship between dark matter and antiparticles. So every particle has a corresponding antimatter particle, and when you bring those together, they combine to produce energy using the formula E equals mc squared. So a proton and an antiproton can do that. Electrons antiparticle is called a positron. They can do that. A neutron and antineutron can do that. We haven't yet found the dark matter particle, but we don't know exactly what its antimatter particle is. So that's the only connection I can think of. Now, Jharna Das has asked me if I can speak in Bengali. আমি নিশ্চয়ই আমি বাংলা কথা বলতে পারি, হ্যাঁ। Thank you. So I can of course speak in Bengali. আমার নাম রাজা। এলিসার সঙ্গে আমি অনেক বছর ধরে কাজ করেছি, 13 বছর ধরে আমরা একসঙ্গে কাজ করেছি। So Elisa, I'm saying in Bengali that you and I have worked together for 13 years. I probably couldn't do that as easily in Spanish. My Spanish is rusty now, but anyway, that's what it is.
We have a question about the different subfields in astronomy that one can apply for, like different posts. But there's so many. What would you suggest for some different areas of astronomy for you both, Elisa and Raja, different subfields of astronomy to study?
Elisa, what have you studied? What subfields have you studied?
I didn't get the question, sorry.
So what subfields of astrophysics can one study? You've studied a few different.
So you can, no, I have been always in galaxies. Yeah, local galaxies specifically, but you know, I have done more massive galaxies and less massive galaxies, and now ultra diffuse that we actually don't really know where they are because of the dark matter. And yeah, but you know, there are many fields in astrophysics. I specialized in galaxy formation and evolution, but you know, there are so many other fields. Yeah.
And Elisa, you haven't always studied this in nearby galaxies, because remember, you got this project approved to study the Pandora's cluster, and that cluster has become so famous now because James Webb has it, and it's become so famous. Remember, you were studying globular clusters in that cluster. So the way I like to think of it, you know, all of you are in front of a computer and you're looking at a Zoom screen. The Zoom screen has created a grid, an X and Y grid. You can divide astronomy into an X and Y grid. You can think of the rows as different areas of astrophysics. One row could be planets in the solar system. Another row could be asteroids in the solar system. Another row could be comets in the solar system. A row could be the sun. Another row could be other stars. Another row could be clusters or families of stars. You notice that I'm going from small to big. I should have started with asteroids, comets, then gone to planets, stars, binary stars, so pairs of stars, clusters of stars, small galaxies, large galaxies, collections of galaxies. I was showing you pictures of a collection of galaxies called the Virgo cluster. There are smaller collections of galaxies called groups. Elisa and I have been studying groups in the Pisces, the Pisces survey, the Sculptor group, the Sene group, the M81 group. And then you can study superclusters of galaxies. Then you can study even larger scales. The afterglow from the Big Bang would be a very large scale. So you can think of every row as a different part of the universe, different physical part of the universe. The columns are different ways of studying the universe. Some people study the universe by doing calculations, so that's called theoretical astrophysics. Some people, like Elisa, Eric, Rosalie, and me, we study the universe by making measurements of the universe. That's called observational astronomy. Some people study the universe by building instruments, by building telescopes and cameras and spectrographs. So that's why I think of astrophysics as a grid. The columns are different techniques for study, and the rows are different parts of the universe that you can study.
Thank you so much for that. Have quite a few comments. Let me go to one that is asking about observing. What is our current status? Roger, you were sharing a few screenshots with us from Elisa and Eric. What's going on now with the observations?
Elisa, you'll be able to answer that based on the other Zoom call.
Sorry, what?
How are the observations going? How long are the exposures that you're taking right now?
So we are doing exposures of 20 minutes.
Okay.
And we are observing, because our galaxies are so big that they fill up completely the field of view of the telescope, the instrument that we are using on the Keck telescope. Then we have to move away to observe the sky, because when you are observing the galaxy, you are observing the galaxy and the sky on top of it. So to analyze the galaxy, we need to remove the sky so that we have only galaxy in our image. So we have to observe the object plus sky, and also sky separately. So then do that subtraction and get a clean image or cleaner image of only the galaxy. So we're doing right now that in that pattern of object, sky, etc. Yeah. And every exposure is 20 minutes. We are going to observe for 6 hours the same galaxy.
I see. So it's 20 minutes on sky and then 20 minutes on the galaxy, 20 minutes on sky. Is it alternating like that, or are you doing two 20
We are doing
minutes?
object.
So you're doing sky?
No. We're doing object, sky, object, sky, object, sky, object. That's the pattern. And each exposure is 20 minutes.
20 minutes. So you're...
So 20 minutes object, 20 minutes sky, 20 minutes object, 20 minutes object again, sky, object, and so on.
So except for the beginning and end, you're doing 2 times 20 of objects in a block, and then... got it.
Yes.
So you get twice as much exposure time on object as on sky overall. And when astronomers talk about sky, it means something very specific. The Earth's atmosphere actually glows. During the daytime, the Earth's atmosphere reflects sunlight. That's why it looks blue. But even in the nighttime, when there's no sunlight reflecting off the Earth's atmosphere, it glows. And that's what Elisa is referring to when she talks about sky. The Earth's atmosphere glows.
Okay, so we just left our guys there. It's staying relatively in the same spot.
Could you maybe even further talk about sky subtraction, Raja?
Yeah, so that's exactly what...
So we do not have signal now?
We don't have the guide star quite yet, but it's coming in and out, but it's not consistently there to guide reliably on it. But it's in the same spot as it was when we were guiding.
Yeah.
So, I think we're still on target,
Okay. So I'm gonna wait then a few seconds, and if we don't have any signal, then I will abort.
Abort. Okay.
Okay.
So what Elisa was talking to, the person Elisa was talking to on a different Zoom call is actually on the mountaintop in Hawaii, on Mauna Kea, at the Keck telescope, inside the building of the Keck telescope. And he was saying that the clouds are rolling in and they're not being able to, oh, please don't annotate. Whoever's annotating, please stop. Right. Yeah, so we've run into clouds, and that is hampering our ability to make measurements right now. So sorry, Jamika, you were asking a question about.
Oh, yeah, we're just the sky subtraction and why that's important to do.
Okay. Yeah, let me so when you take a picture of let's say a galaxy or a star, not only are you getting the light of the galaxy or star, but you're also getting the glow of the Earth's atmosphere that's in front of us. So the Earth's atmosphere is transparent, but it's glowing. If you can imagine that. It's transparent but glowing. So we can look through the atmosphere at the light of a galaxy, but what our silicon device picks up, the silicon detector picks up, is the light of the galaxy plus the glow of the Earth's atmosphere, both of those things. So in order to remove the effects of the Earth's atmosphere, every so often, Elisa and Eric are pointing the telescope away from the galaxy to a relatively clear patch of sky, and then they're coming back to the galaxy. And the reason we do this often is because the glow of the Earth's atmosphere is not constant. It's changing with time. It's changing because the conditions in the upper atmosphere are changing. The humidity is changing. The chemistry could be changing. So humidity, pressure, temperature, as these things change, the glow of the Earth's atmosphere changes with time. So we keep monitoring what the glow of the Earth's atmosphere is by going away from the galaxy and pointing to a blank patch of sky. When you have a blank patch of sky, almost everything in the image is dominated by the Earth's glow, and there's not much astrophysical, there are not many astrophysical sources there. So that's how we account for and subtract off the glow from the Earth's atmosphere. The glow from the Earth's atmosphere is sometimes called air glow also, because it comes from the air in the Earth's atmosphere, the glow of the air in the atmosphere. And you're probably wondering, why don't we see the air glow at night? It's because it's too faint for our eyes to see, but it's bright enough for telescopes to see.
And so, Raja, thank you. In the last few minutes, you, if we could maybe swing back to some of those last images you were showing. We've had some people leave and some people join in the last 10 minutes or so who may not have heard your wonderful explanations about those screenshots.
Sure. These screenshots over here.
Yes.
Let's see what yeah, so let me start with this one. You can see these horizontal bands over here in this blue screen on the right. And this near vertical line is it's called a cut. What we're doing is, by drawing this line, you can ask the computer to tell you what the brightness is as a function of position along the cut. That is what is shown in the graph on the left. You can see that it picks up these peaks every time. These peaks correspond to these horizontal rows over here. So it's a little complicated to explain why it looks this way, but it's really a spectrum of a star seen through an integral field unit. And because the star is not point-like, the blurring of the atmosphere causes it to appear on what are called multiple slicers. At this point, I'm unfortunately getting into very technical terms about how an IFU works, an integral field unit works. So that's what this screen shows. This one is showing you the spectra. I don't know if you can see, but there are these vertical lines. These are produced by the glow of the Earth's atmosphere. This is what we were talking about removing. These more or less random streaks, they come from something called cosmic rays. These are high energy particles that are striking the silicon detector. This is a view of the camera that is used to sort of guide. It's a side camera, not the main telescope, but to guide where we are pointed. It's almost like a finder camera. And this again is the guide camera, a slightly different view of it. This box on the right is telling us where the telescope is pointed. You'll notice that the coordinates of the telescope are fixed. They're not changing with time, but even though the Earth's rotating, the telescope is moving constantly to compensate for the Earth's rotation. If it didn't do that, these coordinates would keep changing with time, because if the telescope was static and the Earth were rotating, it would point at different galaxies, would point at different stars or galaxies due to the Earth's rotation. So the telescope has to rotate has to move equal and opposite to the Earth's rotation when we are taking a long observation like this. Was that okay, Jamika?
Oh, that was absolutely wonderful. Wonderful. And in these last 3.5 minutes, I will say that in the chat, we're getting a lot of thank yous for the informative and engaging sessions, for the background that you all shared on your past here. There was a lot of jubilation hearing you speak in Bengali as well too. I will say that we had several younger students in the session, some teachers with students and parents with students as well. One who specifically said that her daughter is an aspiring astrophysicist. So we are so thankful to have all of you with us today, and we look forward to having you in future sessions. So in these last 2 minutes, Raja and Elisa, since the weather has become challenging, how will you proceed?
Well, we will, unless the weather gets really bad, as in rain or snow, and the telescope needs to be shut down, we'll wait out the night. We'll wait for periods of clarity. If it looks like there's a threat to the telescope, if there's any chance of precipitation, then of course we have to close down the building. The telescope sits inside a dome, and the dome has an opening to it. Right now the dome is open, the telescope's looking out, but if ever the humidity goes up and there's any threat of precipitation, then we have to shut down the dome.
Fantastic. Thank you all so very much. And I will say that we have another session in 4 hours. So we'll be joining Elisa and Raja and Eric at the last few hours of their observations, as well as again tomorrow at this same time. So those registration links are on our Shadow the Scientist website. Please feel free to join us. And several of you have directly messaged me about the recording for this session and the transcript. For those of you who asked for the transcript, I shared with you my direct email address. Please just email me and I'm happy to share the transcript with you. As far as the recording, I will edit it and it should be ready in the next few days. That'll be posted, publicly posted on our Shadow the Scientist YouTube channel. If you are a subscriber to our YouTube channel, you will definitely get a notification when a new video is posted. Yes, and so it's the top of the hour. I will pass it over to Elisa and Raja to close us out.
I am just, sorry, Elisa, go ahead.
Oh no, I just wanted to say thank you for everybody to everybody for being there and for being curious about what we do as astronomers. And you can see that we are not peeking through the telescope anymore, but we're looking at many desktops in a very big computer. So thank you for being there.
Thank you, Elisa. I'm putting some information in the chat about, people have asked about internship programs. Yes, we do have something. Elisa and I have both been mentors for this program. And I've put information about that. They're also available on the website that I put there. You look for, I'll put the website again, Science Internship Program it's called. But you know, it's for this year, the application portal is already closed. You should apply early next year. But it's a long program. It's a 7 to 9 week program. And most, you have to check to see if your school has summer holidays that are aligned with that or long enough for you to take part in that. Yeah, they're not stipends, but there are scholarships that cover, make it zero cost to the students. And we have had students from India take part in our program in these internships. Thank you. Thank you all.
Thank you all so much for joining us.